he graduated from this university and as a doctor of philosophy from the University of Oxford.
Yes, I think so.
He is a superior researcher in CONICET and CONEA, and founded director of the ITEDA.
Yes.
And he's involved in many important experiments in the region. He will tell us about this.
Yes, yes, that's right. Okay. Good afternoon to everybody. Yes, I'm going to give this talk about large international astrophysical experiments in Argentina. So we are in ITEDA. We are actually focusing on that because it's well, it has several advantages, right? Actually, if you want to study frontier science to a certain extent, and you need to do experiments, it's good to have international laboratories. I remember with the Piaget project that the head was Jim Cronin, which was who's going to tell me about time? Okay, right. So he was a Nobel Prize winner, and I asked him was young and inexpert at that time. I asked him, how do you win a Nobel Prize? And he said, if you have the best detector system, which to a certain extent is true. I mean, in order to do a experimental frontier science, I think you need to have a frontier detector equipment, and for that you need to have an international collaboration. So we are actually focusing on that issues. The Piaget Observatory, and that's the internet, the web address, .org. So you can get more info if you do want to know. Then the cubic, that's in Mendoza. It's a province of Argentina, which is on the west, the Andes region. Then the Cubic Observatory, which is in Salta. It's another province, which is in the northwest also. Then the Andes Laboratory. This is an underground laboratory that it's a project. So construction has not started. So it's until you see a guy making a hole with a shovel, then it does not exist, right? But we are already making prototypes, and I'll let you know about them. But it's a project. Then the other issue in ITEDA we pay a lot of attention is outreach, because I take it as a way to return to the society what the society does for you. So it also it's important to promote science between high school students and all that, but the main issue is try to return to the society. Actually, in Malargüe, we have a visitor center which is visited by 8,000 persons per year, which is roughly the population of Malargüe. So it's a scientific visitors place. So science can also be interested for visiting. So they see a laboratory, they have guided visit and so forth. And also we have our main interest, it's human resources, which is one of the reasons I am here. I'm trying to attract your interest. So we have double degrees with Germany, KIT, which is an excellent, one of the few excellent universities of Germany, with UNSAM here, University of San Martin. And then we have students that do both, stays 1 year there and 2 years here for their PhD research. And we have professors that come and go from both places. And we want to start now, we're trying to start with Rome now. Università Tor Vergara in Rome. This is Rome for cubic and KIT. Currently, KIT is essentially, it's only OJ. So we'll see how this evolves. Okay. Nitera is CONICET, CONEA. So this is a very, very good thing. That CONEA was the first institute between CONEA and CONICET. There was no institute prior to this between CONEA and CONICET. But this is, it helps a lot because CONEA has the budgets and CONICET has the human resources. So if you want PhDs or staff members, CONICET can actually provide that. And UNSAM gives us the academic umbrella. So if we want to do a double degree, that is issue a PhD degree from both countries, we need that. For that we need time. And it's budgeted by the Secretaría de Políticas Universitarias. So, but it's of course open to anybody. So we have double degrees from Bariloche, and it doesn't need to be from Itera. So if there is an interest, we could talk. Okay, so this is it's a stamp, an envelope for postal stamp. When we inaugurated OJ about 20 years ago, you see 75 cents. There's a bit of an inflation nowadays, so that might not be enough, right? So, but it actually caused an impact when we inaugurated the PROJ because it's international, it's a lot of people, it's many countries, 18 countries, so it's the science aim. So what we are trying to do now is to create a new branch of science, which is charged particle astronomy. When you are working at very high energies, then the electromagnetic fields, cosmic electromagnetic fields, will not deviate the particle, it will impinge on Earth. And if you actually find the arrival direction, you could pin down the source and do astronomy in that, study the source with charged particles for the first time. This is what we aim, right? So everything, as you know, in science, until you really do it, you cannot be certain. And then we want to understand hadronic interactions at the higher energy, and we know they are wrong. We measure the number of muons, they are totally wrong. With simulations performed with the current hadronic forces, they are wrong. And here you have, these are the telescopes. We have a surface detector, and we have scintillators. And this is what we work mainly is Amiga. It's underground muon detectors, and then it's antennas that detect electromagnetic information. So I will certainly concentrate on this, on those three pieces of tube. So let's carry on. Okay, this is, it's 18 countries, as I mentioned. Here we are. This is Cronin. This is the Nobel Prize, head and shoulders above all of us. It's not with us anymore. This is for the different countries. This is a friend of mine in those times, Johannes Blumer from from Germany. We've been working together for many years. And these are the countries which are there involved. Argentina, probably, Germany, Italy, and Netherlands might be the most important ones. They're all important, but just pin down some of them. So this is a photograph is in Malargüe, where the observatory was built, and it's currently in operation. So this is just to have an idea. They come from outer space, the cosmic rays, and they permanently hit our atmosphere. There is a number there. And in 1912, Victor Hess got the Nobel Prize for this. He went with the globe and saw there were more and more cosmic rays, so he realized they were coming from outside. And he got a Nobel Prize for discovering that they were coming from the outside to the world. Well, if it is very energetic cosmic rays, when they come on the atmosphere, they collide with the atmosphere nitrogen, and they will create a secondary particles, and they create a shower. So that's good, because as energy increases and increases, the flux is less and less. So if you want to detect a cosmic ray of high energy, it's much easier if it spans over an area of several kilometers, right? So we detect those showers. There are many ways to detect those showers, which I'm going to make reference of. Okay, so this is what I started to say. So if it is not enough energy, they will bend, but if it is enough energy, they will pinpoint back to the, and they collide with the cosmic CMBs, and they high masses, they will spallation processes, and there is energy losses for colliding with CMBs. So energy is lost as they come all the way to us. Right. So here we are. Let's see, how do I exit this? Escape. And then where the hell is the life is full of rude awakenings. Here it is. They do not obey me. It has to be your finger, no? Okay, so this is an illustration of cosmic rays. Essentially, is to keep you awake. Here is, they choose Argentina, you see? When we started with this, in Malargüe, they thought that it was a portal, magical portal. That's why we chose that, Malargüe. Well, here it is the surface detectors, 1.5 kilometers, 1,000 kilometers apart. And you see how several of them are triggered, and then you reconstruct the lateral distribution function. And it's all with solar power, right? You cannot bring electricity to all of them. It's 3,000 square kilometers. It's the largest experimental facility of the world. These are the telescopes, 6 of them in 4 places, and they study fluorescence light, the fluorescence detectors. So they are, so escape again, I repeat the path, will this work? Abrir archivo here. Fantastic. Right. So this is actually, if you do very huge experiments, you actually need to have strong support from the authorities, because they involved large budgets. So in order, if you do experimental large observatories, you need to get that sort of support. And without them, it will be impossible. So I'm thankful for all the help. So 20 years, so it's been permanent help, independent of the political color. We've always been supported. So it has been taken as a state policy, the Piroge project, right? So this is when we started. Do we have a pointer? No. Ah, here. Here is where we started. In UNESCO, the headquarters in Paris, 1995, they chose us. We were competing against Australia and South Africa, and they chose us. That's Cronin, you see, counting the votes. And this is me, who is who was the mayor. And this is rubbish. I mean this, not my talk. Right. And this is Cronin, and this is when I was young and beautiful, right? Okay. So this is we were inaugurating the observatory, and this is the picture I show you. And now it's because of our success, they gave us 10 more years, and then we hope to have 10 more years. We'll see. And the agreement was signed, and it's Auger Prime. And the idea of Auger Prime is that it has new detectors. As I mentioned to begin with, in order to do frontier science, you need better and better detectors all the time. This is Nando Ferroni, he's a friend of mine. He was the president of the INFN. This is Barañao, who was the Minister of Science and Technology. It doesn't matter who they are. These people from the international collaboration. Okay, so this is so surface detectors. You have the primary particle. It creates a cascade. These are close to the core. You cannot measure there, because all the systems they just saturate. So you have to be far away from the core. The core, by core I mean where the primary particle would have collided on Earth, the shower core. So we measure muons, we measure this electromagnetic radiation, and also gammas, electrons, and muons. That's what we measured. This is accessible with ground detectors, and with the fluorescence detectors we see the fluorescence light, and this is an iron, and that's a proton, and you see the iron, it's more particles, so they will collide. The first interaction point will be upper in the atmosphere, and it will have lesser fluctuations because it's 56 particles, so lesser fluctuation. The proton is only one particle, and it will have atmospheric depth will be closer to us. So this is a way to distinguish proton from ions. I mean, the idea of the atmospheric depth and the idea of the longitudinal development, the width will give you it's one of the two important ways to distinguish the primary composition. Well, this is the observatory. these are the telescopes. There is one there, one there, one there, 6 each, 30 degrees each, 180 degrees, and they look inside. So you could have the fluorescent detectors, if it is high energy enough, more than one detector could actually be detecting. So los leones, coigüey, coloma amarilla, y los morados. And here is the central campus, where the central campus is where everything by telecommunications, you can see a telecommunication tower there, they will send the surface detectors, they talk to itself, because they need to define a trigger. When the trigger is satisfied, then send all the information to this and to one of the 4 antennas, and that is geared toward the central station to the rest of the world, 18 countries of the rest of the world. And now we do have another, this we started in Itera, to go to lower energies. It was our idea to go to lower energies, and so they built new detectors looking up, because lower energies, they will not reach those closer to Earth. So you have to look up on them. They are 60 degrees above. And this was our idea. It's in here. So the closer distance, if you want to detect lower energies, you need the detectors closer. So 750, half, and then 453, even lower energies. So you can, but the spectrum goes as e to the -3. So you need, if you would go 1 order of magnitude less, then you need 1,000 times less. So the larger, if you want to go to the extreme largest energy, which I think are the best, the more important ones, then you need a very, very huge detector. This is what we have. This is our muons. This is our idea. So not only we go to closer distances, but also we realized that you need to measure muons, because muons alongside the telescopes are the ones that can identify the chemical composition of the primary particle, because depending on what the particle is, the number of muons they will produce. So we came to that idea many years ago, and at that time was not very much accepted, but nowadays it's totally accepted, in as much that they want to have scintillators on the surface to distinguish indirectly muons from electromagnetic radiation. Indirectly, because if you put them underground, it's direct, because only muons go 2.5, 2.3 meters below ground. They are very penetrating particles. So we can detect them directly. We say it's a muon, but it's much more expensive because you have to go underground, right? This is what I mentioned, the radio stations, which is also. So when we decided to upgrade our J prime, is it making reference of this? Well, probably some time later. Okay, this is also something surprising. It's 11 orders of magnitude, and if you plot the cosmic ray spectrum, it's essentially a line. It's multiplied by e to the cube, but it's essentially surprising what nature does. It's the flux in logarithm paper. It's a flux. It's a line. So we want to study this region, which I'm going to show now in more detail. Okay. Okay, here is more detail. This is the Auger domain. This is Amiga. Auger was starting here. We went essentially 2 orders of magnitude below. And essentially you can see the second knee, and you are in closer contact with the stern hadronic interaction. So you have a bit more of an anchoring point, right, for the hadronic models. It's not enough, but it helps in a sense that you have a better idea of what hadronic interaction to use. They have started now with this, but we don't have the hadronic forces for that. Okay, so this is the different regions, so we are concentrating on this, particularly us in Itera. Here it is. So the idea is that what is the science? Why is this taking place? Why do we actually, this is multiplied to the cube. And here it's not a straight line, right? So there are issues, and those traits in the spectrum should guide you towards the physics behind it. The suppression is probably because, yes, there is no source in the universe, energy source, capable of going above that energy. So there is a suppression. In the younger days, they thought there was. Auger actually made the measurement, said that was wrong. There were Agasa in Japan and Havila Park in United Kingdom. They said that there was no suppression, but we measured with detail there is a suppression. So this is probably because there is no enough energy. So we are going, once we get all this, we're going to do a spectrum composition and source distribution combined fit in order to understand how things are going. We do have some idea, though. This is just published by Itera in the ICRC, July 2023. This is the second knee. So this is Amiga in-field array. Amiga is Auger muons and in-field for the ground array. In-field because, as I mentioned, it's 750 and 433. So this is all the in-field results, these two. Right? And so we see the second knee clearly. This is the this is the fit. It's a smooth, soft transition spectrum, and those are the two spectrum indices, right? So we currently believe that it's a transition from galactic to extragalactic source. Now this is, as I mentioned, Amiga. So we designed this. So we decided to use scintillator bars. So a muon goes through the scintillator bar. They're called scintillators. They will produce light. The light goes into an optical fiber, which is underneath this aluminum foil. Once it scintillates again and produces a green light. And the green light cannot escape the fiber. So it's produced total refraction. It cannot escape the fiber, and it has to go to one of the ends. Where? Well, it goes both ends, but the only one that we care about is where the photosensors are. Actually, we painted black the other end because bouncing back will handicap the timing of the issue. So it has 64 bars, 32 and 32, and we started with an engineering array which has 2 of 5 square meters and 1 of 10 square meters because we wanted to see the efficiency. So in here you say that the one with 10 square meters and the one with 5 square meters, they measure the same amount. So it's a slope 1. So it's we came to the conclusion that it's 99% efficient. We're very happy with that. Well, this was every time you design something, you have to do it firstly with simulations. You have to simulate. It's a lot of work. But then after simulation, you actually have to do the experiment. And that's the engineering array. That's the idea of the engineering array. Once the engineering array works, then you can carry on. Here it is. You see, this is the scintillator bar. This is the optical fiber. And we asked Fermilab to produce them for us, which was fantastic, because they do it for no profit. So they have all the machinery, they have everything to produce the scintillators. They do the coating, they do everything. They charge us all the manpower, and they charge us all the goods that we need to buy. But it's probably will be impossible if you do it with a commercial provider. Here is the engineering array. We decided to do that. One in the center and 6 around. You see how it's here it's the 5 meters and the 10 meters. So this is you have to be careful. One of the most important things is what we call the clipping corners, because sometimes, depending on how it's oriented, if it is like that, or if it is like that. If it is like that, the impinging particle, there is no clipping corner. But if it is like that, it could actually impinge in both scintillators. So you have to do that take into account. The production phase is now been translated to Malar. We don't do anymore, because ITEDA does research and development. So when we go into the production phase, we don't do it anymore. We hired people that do it in Malawi, which is much easier because it's where they are. So we don't need to transport the detectors. They just our technicians and engineers, they are researchers too. So I start to research in another project, nowadays in Cubic. So once they finish the prototyping and the engineering array phase, we leave it aside. That's the way it has to do. It has to be. So because it's so production goes to, and I'm doing an excellent work. You see, you have to do all those enormous wells. Here they are. It's one thing that we learned too is in the engineering phase is these are binary. We call them binary channels. So it's segmented, because if there is a signal, 1 muon arrived, and it is segmented after a certain distance from the core, you know that there cannot be more than 1 muon. So there is an inhibition window. So we set it to 20 nanoseconds. So in 20 nanoseconds, in one of these bars, there cannot be more than 1. This is all simulations, a lot of work, but we came to that conclusion, and we adopt that, and we think we're right. But then we realized in the engineering phase that instead of a 0-1 electronics, 0, no muon, 1, if it is above this threshold, 1 muon, 0-1 electronic, binary channel. When I started with this, I thought this is stupid, so easy to do. Then it took 10 years, 10 PhD students, much more. Deal with reality is much more difficult than dealing with that. Then we decided to put an ADC channels, not only digital, but adding all the signals. So when we get close to the core, there is enough signal as to have a well-defined charge recollection peak. So by measuring the mean value of that charge peak, we know the number of muons. And the other beauty is that we can actually calibrate the ADC channel by the binary channel, which is fantastic. We know when one muon arrives because we know the digital channel, and then we know the charge of one muon in the ADC. And we do enough statistics, we can calibrate. And that was one of the reasons why we won an international competition. I think I will mention that now. So all this has been done in Italy. Okay, this is the deployment. You see, well, we have to make the holes, and they have to put, and then we have this that will allow access to the electronics. So there is something that was burned, a chip needs to replace. You pick it up, take it to the central station, replace it, and put it back again. So you don't need to actually make a hole. And the scintillators will never break. And if they break, tough luck. Okay, so here it is. The hole, they put it, and then they carry it back and leave the holes up there. Okay. This is the typical binary trace. You see, we decided to put a threshold 1, 0, 1. So it's each bin is 3.9 nanoseconds. And then in order to have a signal, it's this. And then this is not a signal, this is noise. That's one of the things I mentioned when I thought it was very easy to say 1, 0, 1, 0. Then we can, with reality, all the signals from the photosensors, they don't come at the same time. So when the muon produces scintillators, they do have a delay time. So it's about, say, 20 nanoseconds. So they are not produced all the fibers light immediately. They take it a time. It's a width. And that 20 nanoseconds is an inhibition window. So when I started, I thought that all the signal was in a single peak. No, it's in a peak that lasts longer. So this is then we decided to use this idea 1, 1, 1, 1, 0, 1. So that's a peak. If this is 1, this is noise, and it's working fine. 32 strips. On each side, 4 meters long. Here it's biparametric with the muons, with the telescopes. Here, you see? These are the telescopes, and these are the muons. So this is, we are lacking a lot of muons. So the hadronic interaction is wrong. It's simulations. These are simulations. Simulations do not reproduce the actual data. So these are different energies, the in-field energies, and apparently it's close. It's close to helium, so it's low masses, low charges. But it's about 40% wrong. So we need to make efforts. I didn't mention, but maybe so we competed with Amiga in the Prime Auger with new detector system with 2 other international projects which were called Tosca and Marta. I just want to make reference. One of them was Tosca, and they wanted scintillators, but they didn't have the binary channel. So they lost because without the binary channels, you cannot calibrate the ADCs. You don't know what is the energy, that the charge that produces by immune. So calibration is always the name of the game. In cubic too, everything. If you don't have a calibration, you don't know what else, what are you measuring. You don't have a rule. You don't know if it is 20 centimeters, 30, you don't have an idea. So that was the main issue. So maximum and new numbers, it's flowers, showers. Okay, charge particle astronomy. Tosca and Marcia, to be part of Auger Prime, we won. And we are organized in working packages or tasks. So simulation and data analysis, scintillator modules, photosensors, which are now silicon PMs. Telecommunications, you need telecommunication because you need to transmit the data. The electronics, you of course need electronics. Photovoltaic system you do need because you cannot, you don't have electricity in the middle of nowhere. And astronomy, astrophysics always is in the middle of nowhere. You cannot measure in Buenos Aires. Might be some pollution around, right? So you have to know far away from everything, right? Deployment, outreach, and the administration and costs. That is very important too. For large experiments, this is millions. So you need administration, and you need to have accountants, a lawyer. You need to have an administration core, because if not, you end up in jail, which I will not enjoy very much, I presume. Okay. Right. So Pierre brought Cubis and Andes, because actually Cubic, they came to talk to me, Stavros Casanevas. Because of Auger, we gained some sort of international respect, because this was working for years. And there were times in which there was a corralito, a corralón, whatever, but this kept on working, right? So it's, and so they came and talked to us for Cubics and now for Andes. And it's management, administration, scientists, and technicians. Whatever leg you miss, you are dead. I mean, if you don't have any of those, it's not only scientists as physicists, also scientists as engineers. So I call a scientist everybody with a PhD, whether it's an engineer, an astronomer, or an engineer. Cubic. So this is what we are dwelling now. So we're trying to get information from the inflation era of the universe. Fractions of a second after, well, people here that know 10 times more than I do, but it's not easy. So it's every time you get into a frontier, science frontier experiment, it's like a principio de incerteza. The possibility of getting the result, the possibility what you do if you get it has to be about 1. So it's the possibility of getting a good result, it's very close to 0. But if you actually make the discovery, it makes a difference. It makes a difference. So that's the way I like to work in things. So taking the risks. So it's you have to always walk near the abyss, but it's good fun, right? If you don't fall. Okay. So let's see. Well, it's an international collaboration. It's 10 to the minus 35. That's a guess, I presume. Well, it can be based on theory, but okay. We are using bolometers, which come from the GRIMS. It's light beam measurement, okay? And we close zero, yeah, zero. So the CMBs are 2.7 Kelvin. So we are working close to 0.3. Yes, go ahead.
Yes, the bolometer is an instrument because, for example, we analyze the light from a star. The bolometer allows to avoid the errors mostly due to another wavelength. So the bolometer is a filter that allows us to measure the light of a star, for example, at wavelength specific.
I will come to that point. That's interferometry. We'll come to this point. So sometimes they don't. So it's BISEC actually thought they discovered this, but since they didn't know the frequency, they were wrong. Okay. So here it says what you mentioned is the qubit is unique in the sense that joins bolometer and interferometry. So you do know the wavelength of what you are measuring. So we think that this will be an important difference. So simulations, everything says yes, it does. So we have to measure and see how things work. Then the observatory was inaugurated in November 2022 in Altos Chorrillos, Salta. And once you measure the CMBs, you can get the Stokes parameter that actually will tell you the light polarization, the B modes and E modes. Okay, universal inflation. Well, I put an interrogation because until you measure it, you cannot be certain. So you need to, science is observational, so you need to measure it. And if you actually find, and this I think the B modes, there is a certain amount of trust that it's unambiguous. If you detect the polarization, the B modes, there was inflation. So that's started with Alan Guth, and then others, and so they explain that it's a flat universe. So you've been listening to this. Flat straight lines keep essentially parallel, and uniformity essentially that in both homogeneity and isotropy. I think one of the fathers of this is Matthias, no? Are you here, Matthias? Oh, Matthias is okay, right. So it's, okay, right. So this is one of the plots. As I said, 10 to the minus 35, 10 to the minus, it can be true, but it's what theory tells, right? I am an experimentalist. So it can be true, but what the common knowledge says it has to happen. And it says it's 30 orders of magnitude, then the universe increased many orders of magnitude. Eh? So if increases that much, then that proves why it's essentially flat and uniform. If B modes could confirm inflation, definite evidence remains elusive. Well, I trust we could do it, but it's not certain. So as a scientist, so here it is in the middle of nowhere, as I mentioned. If you want to do astrophysics, you have to go to the middle of nowhere. And in here is nearly 5,000 meters above sea level, so when you get there, you wished you were somewhere else, right? because it's not enough oxygen, so very dim. It's much better. There's no atmosphere attenuation, very little atmosphere attenuation. So you can measure, and there's no pollution. So this is where cubic is. It's already there. And okay. Okay, this was inaugurated in 22, it says there. November 22, so it's less than a year ago. Yeah, you can see the bolometer here. This is the shelter, and this is the mount with the bolometer. We designed and built in Itera, we designed and asked private industry to build the mount with the design that we did. So it was good fun. International collaboration is mainly Argentina, France, and Italy. Those are the actually collaborations. There are other countries too, but those are the main. And this is the shelter that opens and closes. So one of the issues that I also want to stress is that you gain knowledge. With OJ, we gain knowledge. Not only expertise and have good laboratories and so forth, but also, for instance, we have to build a shelter for the LiDAR, OJ, to study the atmosphere. So we copy that, essentially, and then we have that shelter. So it was designed, the shelter, by the people of Mendoza, Itera Mendoza, and it was built by us, by National Atomic Energy Commission. There it is, the shelter in the middle of nowhere, and this is the the integration lab. The integration lab was built in Conea by people from Conea. That's another advantage. I mean, Conea has people that used to do, were very much involved in uranium in mines, so they do have the infrastructure. So they have the machinery, they have the people who know, architects, and they build that essentially for free, in a sense that we didn't pay for anything but for the materials. So that's the difference between life or death, right? This is when we signed the. I always like to sign something, because as years go by, then you can actually go back to that agreement that was signed, and they respect it. If it is signed, it says that this is a strategic project for the signers. They will respect that. So this is Campero this is the president of Conea, that's the minister, and that's Urtubey, who was the governor. And this is Lamagna, who is the vice president. It was signed by CONICET too. So it's the minister, Salta, CONICET, and Conea. So it's always the same four. So for Cubic and for Andes and for everything, it's always the fair. The governor, the minister, Conea, and CONICET. That's the idea. Okay, and this is when we inaugurated the laboratory of integration in Salta. Here is Filmos. You can see Filmos. That's Franchi. That's the president of Conea. That's me. And that's the Minister of Infrastructure from Salta. They are just unveiling the commissioning plate. Here are the names, right? So it's that's the inauguration of the laboratory integration. So everything comes there, and then we have to calibrate, to mount, to make it work, to observe the sky before sending it to Altos Chorrillos. Because once you send it to Altos Chorrillos, you have to be certain it will work, because there it's in the middle of nowhere. right? So you have to be certain that things do work. And then, well, that's the laboratory of integration. But then CONICET and the province of Salta were very kind with us. They allow us to share that building in San Antonio de los Cobres. So the central station will be there. And so we have to a certain extent, a fantastic building that we can share with YAMA. And so we have everything we need. This is the laboratory we mounted at ITEDA for quantum cryogenic sensors. So here is the cryostat. This is the electronics we bought. Here's the cryostat. Was installed in December 2022. And here is a sputtering source. So you need a sputtering source in order to deposit the metal, the superconducting metal, on a wafer, on una oblea. And this is that first sensor prototypes made in Germany with our students. We have 6 PhD students, engineering, that do that under the guidance from Germany. This cost us $1.5 million. Okay. This is the actual test, how it works. It has a test here. This is an absorber. It absorbs the signal, the CMB, and then the sensor changes the temperature with a new energy, and it leaves being a superconductor to being a conductor. So it's changing a resistance, changing the current, and that is what's measured. So every time it arrives, so it sounds easy. But we decided to go somewhere else. Metallic magnetic bolometers. This is has been manufactured now. It's that's the electronics we made. These are the people who are involved. This is 80%, but some parts do need more work. But it's so in ITEDA we never get into a project in which we cannot have a main partnership in the design of the instrument, because it's we just don't want to switch it on and off. We want to design and build it. We designed and built Cherenkov detectors, the Amiga detectors, and now we are designing and building cryogenic sensors that can be used in Andes too. That's what I mentioned ago. So once you get the know-how, you can use it in many other projects, right? In some other projects. Okay, so in CONEA we do have a clean room. So here it is. This is the second possibility of MMBs. One possibility is with the absorber, and the second possibility is with antennas, which are being used in other CMB experiments. So it's something we can dwell upon, be to a certain extent clear that it will work. So the antenna can distinguish the frequency. So we can separate in 220 and 150. 220 is the background, 150 is the CMBs we want to measure. And then it goes into the MMBs, and then it goes into a magnetic flux pickup coil. That is what makes the signal. So we are working with other departments from CONEA, and we were able to make the first superconductor of aluminum, which is not what we're going to use, but it's just to gain knowledge. Which you think, here it is. The resistance is 0, and then it goes up. So that's a superconductor. We fabricated that in CONEA, not in ITEDA, but in CONEA. Well, MMBs apparently they are not affected by non-uniformity. So you don't need to have a totally uniform superconductor. Since they live being superconductors, they produce heat. And currently, 2/3 of the time is lost. Currently. That's because they need to cool down the system. MMBs don't have that. And then they have important signal saturation that disable the measurements. And MMBs don't have that. So we'll see, at the end of the day, next year, they will compete. The MMBs and the TESS. They will be installed in the cryostat, and we'll see which one is better. So that's how it works, right? It's not a decision taken, right, 5 minutes. 5 minutes. Oh, Jesus Christ. Well, Andes. Well, it has to be in mines because you want to actually shield everything. Well, this is the Túnel de Agua Negra that goes from here to here. Aquí es the Túnel de Agua Negra. It's 1,700. Can I have 10 minutes? Right. So it's this is what we want to measure in Auger is what we want to get rid of here. Essentially muons, right? Because the muon can be penetrate and go all the way 1.7 kilometers down and be considered as a dark matter. So we want to get rid of that, and know what? We know how to do that. We know about muon detectors. So this is the physics of Andes. Neutrino physics, dark matter, biology. This is essentially cancer, no cancer, because you have no radiation. So you study that. Geoscience, this is a geoactive active region. So you can measure down there what happens. And nuclear astrophysics. So they are, if you want to measure very low cross sections, the best place is that, because you don't have noise from everything else. So, and then dark matter, we want to study this region. This is the region of cryogenic detectors, right? So this is the neutrino floor. So if it goes closer to this, then neutrinos and dark matter will leave signals both alike. You cannot split one from the other, so it's useless. So we want to get the reason because, as I mentioned, we know how to make cryogenic sensors. We are learning to make cryogenic sensors. This is a international projects we did laboratory. This is you can see that that's the director of the university of that. This is the engineering that we did that was paid by the government of San Juan. $500,000 they paid. So we are ready to, if there is a call for tenders, we are ready to go. That's the problem with the tunnels. If in a mine, you can build it later on, but in a tunnel, it has to be built simultaneously. Because if I tell them, just close the tunnel for 2 years for us to study dark matter, I don't think they will like that, because they want to make business with China, Japan, India. Okay, this is the when the money they pay, and this is we signed with Italy, 60,000 per year per part. Here you are, Diana. Okay, at this laboratory. Okay, so in order to brief signal to noise, muons must be vetoed. So we have to veto muons, and we have done this. So we have done the muon detectors. It's here, and they will be used to veto. We are going to study now in mines, and then we are going to use that to veto muons. Here it is, so we built an ITEDA. So it's 3 detector systems like this, XY. So we know exactly 4 centimeters by 4 centimeters where the muon impinges. And then with 3 points, we build the trajectory. And this can be tilted, so it's, we can measure the direction. I have an idea. Conclusions. Muon videos, so we want to install them right away in August. Okay, so it's we're organizing a task with Chile. They're very embryo. So if anybody of you want to join us in Andes or in Cubic, you're very much welcome. You can join any of the 2 degrees with either Rome or KIT. Outreach, oh, I have to go very fast. Well, outreach is the name of, it's very important. So this is Technopolis. They gave us an important place in the main road. And all the central stations will have outreach, and they do have. Here is what we have in Technopolis. You can see the posters that we decided. If you go to Technopolis now, you'll see it. And this is the foundation awakening. This is also very important for us. Without the foundations, we could not work. Because if we want to make a decision, we need to rent another truck. How much do you need? Tata, here you are, rent it. If you go through paperwork in a university or a CONEA, 2 years. And this is immediate. It's immediate. We decide private industry. So we actually what administer is 1.5 million, 6 million of euros per year for the observatory. CONEA gives us a budget of 4,000 euro United States per year. MinSIT gave us this year $400,000. The Ministry of Education gave us $45,000 per year for the double doctorate, and CONICET gave us a lot of subsidies, but the name of CONICET, as I mentioned, is people. We need all the people they have. And CONEA gave us $30,000 to complete the money needed for the double degrees. So without AWEGNA, nothing could have been done, because the paperwork in AWEGNA is immediate. Well, this is the double degree. I cannot show you this. These are the students. These are the first 2 Germans. These are the first Argentinian in KIT, 2015. This is, we have international students. Here's another one. The name of the people. And now, since we did very well, we are now having an engineer double degrees. Which is here engineers. These 2 are engineers. So it's now a double degree in both. So we have 15 granted. We have 20 students, 12 in physics and 8 engineers. We have a review and so forth. So we pay the stay in the other country. So if you are interested here, you have emails where to send your request. Now this is the future I see it, and CMV says has to be also international too. So that's it. So it's all. So it's the name of the game I mentioned. It has to be an international, and you need the support from the institutions. If you don't have the support from the institutions, you cannot do anything. Right. Fine.
The first data is of cubics.
In what? Cubic.
Yes, cubic.
Oh, we do have some data now, but this is an important issue because I cannot reply to you because the agencies, France and Italy, essentially Italy. France also has troubles, maybe more than Italy. But they want an MOU to be signed, Memorandum of Understanding. So I know this is going to be registered, but it's the truth. So it's we paid $120,000 Argentina, and now we need the MOU to be signed, which I hope will be signed shortly. You know that the operational maintenance costs are shared. So this is not a matter of the agencies. It's a matter of the collaborations. Essentially, we need to, because if the MOU needs to be signed, so we do have a draft already. So I hope that in a month or so it should be signed. Did I answer your question?
Yes. It is operational and it is working well.
It is operational and it's working fine, perfectly fine. But as I said, the agencies decided in Argentina to warm it up until MOU, because we are paying the complete operation and maintenance costs, and that and I actually agree, it doesn't make much of a sense. I mean, it has to be shared. Operational costs are shared, needs the MOU to be signed. So it was working perfectly fine.
Yes, I have a question regarding how Cubic is going to tackle the problem of distinguishing between the CMB radiation and the foreground.
Well, it has the advantage of the interference. So the foreground background is centered at 120 gigahertz, and the CMBs that we want to measure 150. So if you actually measure the wavelength, you can distinguish. So remember this,